Hello, everybody. We are going to talk today about what are called Taylor series. So we've been digging in quite a bit to power series and then representing functions with power series. And we've generally been using the tactic that we can use something like the geometric series that we already know, and we have this function that it behaves like on a certain interval. But now we want to take a look at what happens if we try to build them from scratch. So there's quite a bit in this. We're going to go through it slowly. It really does boil down to some pretty simple rules. So there's going to be a whole bunch of theory up front, and then we'll do some examples. And here we go. So let's start by supposing. So suppose we have a function that has a power series representation. In other words, we know that f of x is going to be equal to some constant term plus, right, our typical representation of a power series, right? So one of the questions we might ask ourselves is, can we figure out what those constants are, the CNs, right? That's right. We're building a series centered at some letter A or some number A, right? We'll know that. Can we figure out what these constants are? That's really what this comes down to. So let's do a little bit of work on that. First of all, let's see what happens when we evaluate this function at f of a. If I put a in, all of these terms become 0, except for the first one. And so we know exactly what that first constant has to be. It's the value of the function at the place that we're building the function, the place that it's centered at, the series is centered at. Remember that notion that the series is centered at A, or it's a series about A. Okay, that's great. We've got one constant done. We've only got an infinite amount left to go. So here's a little trick. Let's take the derivative of our function. Right. Well, remember we said about taking derivatives of power series, we can take the derivative term by term. This is a constant, it goes away. Here's a linear term. Its derivative is just C1. What happens over here? The 2 comes down, right? You can think there's a chain rule, but the inner function is just multiplication by 1. So there's no real chain rule we need to mark down. We'll get 3 times C3 x minus a squared. There will be a term. I'm going to write the fourth term, or the C4 term, x minus a cubed, and on and on and on. Okay, so I'm just taking the derivative term by term. So I evaluate at a again. All of these terms disappear. And so the second constant, C1, is the value of the derivative at a. The first one was the value of the function at a. The second constant, C1, is the value of the first derivative, okay? So let me box these important. Remember what our goal is. We're trying to figure out how we could figure out the coefficients if we wanted to represent a function as a power series. All right, let's keep going with this. This is working pretty well. Let's take a look at the second derivative. So now I'm taking the derivative of this function. The first constant, like all constants, to take the derivative, I get 0. Here I've got a linear term. The derivative is just 2c2. And then this derivative, the exponent comes down. I'm not going to multiply them together. I'm looking for patterns here. So I'm going to leave it as written for now. This one will be 4 times 3 times c4 x minus a squared. Meanwhile, off screen, let's pull in another term. We'll have one that's 5 times 4 times c5 x minus a cubed, and on and on and on. Okay. All right, same trick. F double prime of a. Everything over here disappears. All that's left is this constant term, which is 2 times C2. So it's not quite as simple as the first one, where our first constants were just the function at A, the derivative of the function at a, but it's pretty close. So I can rewrite this as C2 is equal to f double prime of a over 2. Let's do a couple more, at least one more, maybe two more. All right, we'll keep going with this way. I'm going to change notation just a little bit. So sometimes we'll write it this way instead of just, right, there's going to be a limit to how many little apostrophes, little prime marks I can fit up here. So I've written a little parentheses with 3 to mean the third derivative of x. Third derivative of f of x. So I'm taking the derivative of this line. The constant goes away. I've got 3 times 2 times c3 plus 4 times 3 times 2 times c4 x minus a plus 5 times 4 times 3 times c5 x minus a squared plus, and on and on and on. Okay. We play the same game. We evaluate the third derivative at a. I get everything over here becoming zeros, and I have 3 times 2 times c3, which means that c3 is going to be the third derivative at a over 3 times 2. Okay. All right, let's do one more by hand, and then we'll see. We'll confirm what maybe we're already seeing the pattern is. So let's look at the fourth derivative. Taking the derivative of this line, the constant disappears. I've got 4 times 3 times 2 c4 plus 5 times 4 times 3 times 2 times c5 x minus a, and on and on and on, right? I'm not writing more of those terms right now, but you can imagine what's happening. There's the 6th degree has been, the one that was degree 6 when we started is now down to degree 2, right? We've taken so many derivatives that each time it loses an exponent, and on and on and on. We evaluate our function at a. In the series, everything past this term and everything past it goes to 0, and we're left with 4 times 3 times 2 times c4, which means that c4 is equal to the fourth derivative of our function at a over 4 times 3 times 2. So there was our expression for c3. Here was our expression for c4. So if we want to generalize this, what I can say is the nth constant in a power series. So if a function is represented by a power series, the nth constant must be of the form the nth derivative at a divided by n factorial. Okay. So a couple of quick things. When we say the nth derivative, we're gonna use the idea that the 0th derivative means not taking a derivative. So that's just the function itself. And also recall that 0 factorial is 1. That means this works perfectly even for these first terms, right? If I take the first or the 0th derivative, that's f of a, divided by 0 factorial, that's just 1, I get f of a, which is what we have here. C1 will be the first derivative of a divided by 1 factorial. That's right what I have here. And on and on and on, right? This is 2 factorial, 3 factorial, 4 factorial. So we looked at all those factorial expressions when we were doing root and ratio tests and all those other convergence tests, right? Which is strange because we rarely see factorials in mathematics up to this point. But this is why they showed up all of a sudden, because we wanted to be able to build these things. And this is how we're going to build them, okay? So let's summarize what I just said in the following way. We have if f has a power series representation, or sometimes people call it an expansion, at A, right? A is some real number. In other words, f of x is equal to n equals 0 to infinity, c sub n x minus a to the n, right? Valid when x minus a is less than r. So all our stuff about power series, we have a radius of convergence. So if we've got a power series expression, or if we know that a function has a series representation, then we know the coefficients are given by c sub n is equal to the nth derivative at a divided by n factorial. Okay. So this is a big step for us, right? We do have this word if up here, right? We don't always know that they're going to have a series representation. We're not going to dig too far into that thought. I'm going to do a little bit on it today, but we're mostly going to be concerned with how to build these functions and assume that they exist. I'm going to give you things that have series representation, and your job generally is going to be to show that they exist. Or sorry, to build them, assuming that they exist, okay? So in other words, let's just combine these two. We can say something like f of x is equal to n equals 0 to infinity I've just substituted this expression for c sub n in where c sub n went, right? Remember, these are constants. A is a number, so I'm evaluating the function or the derivative of the function or some derivative of the function, dividing by numbers. So this is just a constant, right? And now we know exactly the form that constant takes, right? And what this will always look like is f of a over 0 factorial, f prime of a over 1 factorial times x minus a plus f double prime of a over 2 factorial times x minus a squared, and on and on and on, right? So what we usually do when we want to construct these things is we compute these derivatives. Sorry, these derivatives so that we can make these constants, right? And what generally happens, we'll see in a lot of cases, is we end up with a pattern that emerges. And so we don't have to figure out, obviously, an infinite number of them. You see, oh, this is what's going to happen each time. I can write an expression for this. So we'll do some examples of that in a moment. Let's give a little bit of vocabulary before we move on. We call these the Taylor series for f at a. Or sometimes we use about a, centered at a. Okay, so some kind of language like that. Okay, and you'll sometimes hear if a is equal to 0. People call those, we call them Maclaurin series. Okay. All that is when a is equal to 0. It's really not important. Some people just say the Taylor series centered at 0. Some people say the Maclaurin series. It's not a big deal either way. I'm not certainly going to try to trick you with that one, but you might read something somewhere and want to know what they're referencing when they say Maclaurin series, and all you've ever heard about is Taylor series. So these are our Taylor series, right? This is what we've been building to with all this infinite series stuff. Okay. All right, let's do an example of finding one of these. Okay, so let's start with a classic example and a pretty important function for us. Let's find the Taylor series about 0, or the Maclaurin series, for the exponential function. Okay, so we're going to find Taylor series centered at a equals 0. All right, this is our Maclaurin series for f of x equals e to the x. Okay. Now, we're cheating a little bit. I'm assuming right now that this even exists, right? There's no guarantee that this function has a Maclaurin series or a Taylor series, okay? We'll talk a little bit later about how we would go about showing this. But for now, let's just assume that it exists and go through the process of finding these constants. In other words, I want to write down f of x, which is equal to e of x, as right? Remember, I'm centered at 0, so this is like the x minus a to the n. It's just x because it's minus 0. And we're going to use what we just discovered, that we know the c sub n's are equal to the nth derivative at a over n factorial. Okay. This is a particularly easy one to find. Okay. Why is that? Well, every derivative is the same, right? No matter which derivative we're talking about, the nth derivative of x is equal to e to the x, right? Which means the nth derivative at 0 is e to the 0 or 1. What does that mean for this? That means that our constants are 1 over n factorial. Right? And so if the Taylor series for e to the x exists, it must be of the form I'm replacing the c sub n's with what I just realized they must be, 1 over n factorial times x to the n. All right, or I could write this a little more compactly, x to the n over n factorial. Okay. We'll take a look at this series in just a moment in a graph. Let's do one more thing before doing that. Let's take a look at the radius of convergence. Okay. The radius of convergence, we can check with the ratio test. Right? So first, I want to take a look at the expression for a to the n plus 1 over a to the n. This is what my series terms look like. So a to the n plus 1 is x to the n plus 1 over n plus 1 factorial. Dividing by the a sub n term is just the same as multiplying by the reciprocal of the nth term. This is equal to, so what happens? I get factors of x canceling, and we end up with n plus 1 in the denominator, right? N factorial over n plus 1 factorial is just n plus 1. So to complete our ratio test, we take the limit as n goes to infinity of x over n plus 1. X is just a constant. This can slide out in front. It's a constant, let me say that more clearly, it's a constant relative to n. As n changes, the value of x doesn't change, and I get 1 over n plus 1. This limit goes to 0, so it turns out it doesn't matter what value for x we put in, the limit is going to always be 0, right? Another way to think of it, remember we're trying to represent this function. If I put in any number like e to a billion, eventually 1 over n plus 1 is bigger than a billion, and eventually it's a lot bigger than a billion. And so we can get this expression closer and closer to 0 by taking n large enough, which is what this limit says. It doesn't matter how big this is, eventually n gets bigger because we're taking its limit as we go to infinity. This tells me that this series, its radius of convergence is for all real numbers. right? Sometimes we write r equals infinity, even though that's a ludicrous thing to write down. It just means there is no finite radius. It's good for all real numbers, okay? And so we found a way to write the exponential as a power series, or at least we think we have. I haven't proved that it exists yet. It does, but we'll talk about that in a moment. Let's take a look at this series in graph form. So here we go. So here's a graph. I believe we've actually looked at this one before because we threw this series in earlier videos, but now we have a little more context maybe to understand it. The blue line is the exponential. The green line is the series that we just talked about, right? I've got it over here on the left-hand side. However, I'm only looking at the first term right now, right? The first term would be 1. So it's just the expression y equals 1. Now, of course, I can't show you what happens when I have infinite terms because the computer cannot add up that many terms, but I can start to add terms when I add the first term. So now I've got 1 plus x. This is our linear approximation. As I add more and more terms, this series is becoming better aligned to this graph, right? Now it's off, well, there we see it going up eventually, but I'm only at 40 terms, right? So if I had more time, we could keep going higher and higher and higher, and we would see this, the green line, which represents the series, getting closer and closer to this exponential, right? Also, I should point out what's happening is our series doesn't necessarily match our function in all these places where it kind of looks like it does. It's just that we can't see it close enough. Every time I add terms, I'm getting closer to matching everywhere. The only place I'm guaranteed to match all the time is at that first, at 0, right, where we build it. Everywhere else, it's an approximation. Occasionally, it might hit the line here or there, but everywhere else, it's usually an approximation. And as we add terms, we're getting closer and closer and closer and closer to the real values everywhere, which we can see more explicitly out at the ends where it doesn't match very well in the beginning, right? If I look at x equals 8, my function's down here, my series approximation is up here, but as soon as I add a few terms, that approximation becomes much closer. So again, we haven't proved that this series actually is equal to this function, but I've certainly starting to feel like it does based on how it looks here, okay? So let's dig into that problem a little bit. So I want to be clear, I'm not going to spend a lot of time in these videos, nor expect you to be able to do a ton of this this stuff here, but I want you to see it once, this idea of how do we prove that a function has a Taylor series or a power series expansion, okay? All right, so let's go back to the paper. So let's do something here. So let's keep looking at our series. So right now I've got this idea that e to the x is equal to x to the n over n factorial. Let's write this out a little bit, right? When n equals 0, this is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, and on and on and on, right? That's the idea. Okay. Let's just look at what we've written here. I've written this expression over here equals this infinite series. When we've been doing infinite series and we write some expression, some infinite series adds up to a number, what do we really mean? We mean the sequence of partial sums has a limit that approaches that number. We kind of mean the same thing here. We want to look at the partial sums of this series, okay? So let's start with, I'll call it T1, okay? What I mean by this, what we call this is the first degree Taylor polynomial. So in general, we'll call these things the nth degree Taylor polynomials. Okay. They're really just partial sums. The first partial sum well, it's really the second partial sum. The first partial sum would just be 1, but we usually start at the first degree. This is our linear approximation, right? Remember when I was just showing you those graphs, as I added terms, we started with a function that was just a horizontal line that equaled the value of the function. That would be the 0th degree, y equals 1. It just hits our function at the value. The first degree is a linear function, right? The degree of a polynomial is 1. That means it's linear. That's the tangent line approximation. The second degree Taylor polynomial right? This is now a quadratic function that approximates our function, right? Or yeah, this is the quadratic approximation that approximates e to the x. Let's do one more and then go back to the graph with these in mind. X to the n over n factorial, 1 plus x squared over 2 factorial plus x cubed over 3 factorial. Our third degree, right? This is a cubic function, a cubic polynomial right here. It's our third degree Taylor approximation, our third degree Taylor polynomial. So let's go back to the graph for a second. Just kind of do the same thing we did a minute ago with some of this in mind. Let me zoom in a little bit. All right, it's reacting unpredictably. All right, that's probably good enough. All right, so let's go down. Here's the 0th degree. This is just that constant term y equals 1, okay, which is not much of a function. Let's maybe write these out on this screen. So our first approximations we did just a moment ago, we had T1 was equal to 1 plus x. T2 was equal to 1 plus x squared over 2 factorial. And T3 was 1 plus x squared over 2 factorial plus x cubed over 3 factorial. Okay. So if I change k to 1 here, there's our tangent line approximation. This is T1, 1 plus x. This is the tangent line that you built in Calc 1 to approximate this function here. Let's increase k to 2. Now we're looking at T2. This is a quadratic. Look at this is a quadratic that hits our graph right at 0, 1. And it also matches up nicely with our function for a longer time than the tangent line appeared to, right? There's the tangent line. It's kind of wrapped a little closer around it. Maybe we'll zoom in a little bit. Oh boy, the zoom on this is real touchy. All right, so we go from 0. There's our tangent line. Then we wrap around a little more with that quadratic, right? In other words, remember we matched derivatives to build this. We've now gone, the first derivative matches the slope, that's the tangent line. The second derivative matches the concavity. This quadratic has the same tangent line as our function at this point, and it has the same concavity at that point. It's a better match. Then we did the third degree. Let's go up one more, right? So you can see now in both directions, here's the quadratic, here's the cubic. We're getting a little closer to this exponential, okay? So we won't go any farther right now than the third degree Taylor polynomial, but we can see that we're getting closer to this function. And the idea is, for every value of x, if you compute these Taylor, these nth degree Taylor polynomials, for every value of x, the sequence of partial sums leads to the value of the function at that value of x. Okay, there's kind of a lot of moving parts here, but It's a whole bunch of partial sums, just like we were doing in the beginning of the quarter. Okay. All right, let's go back to the paper now. All right, so we've got these partial sums, these nth degree Taylor polynomials. Sometimes people write T sub n will just be the sum from k equals 1 to n of x to the k over k factorial. It just means, in this case, 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and on up till you get to the nth degree. Okay. All right. So it's going to get a little bit technical right now. Okay. So I'm going to go through this once. I'm going to reiterate, this is not a big focus for us. The focus for us is going to be on building these things. I'm going to do 2 more examples of building after I get through this technical stuff, and then a whole separate video where we just build more of them, because that's the big thing. But I do want you to see this once. Okay. So let's move forward a little bit. We're going to define something that we'll call the remainder. Okay. The remainder, or more specifically, the remainder of the nth degree Taylor polynomial. Okay. So we'll call this R sub n of x. And all it is the difference between the actual function and the approximation by the nth degree Taylor polynomial. Okay? That's all this is saying. Right? Another way we can think about it is that our function is equal to the Taylor approximation plus the remainder, right? Some people call this the error, right? It's just the difference between our approximation and the real thing, okay? The idea is, if the remainder goes to 0 as n goes to infinity, then the limit as n goes to infinity of these Taylor polynomials is actually our function. Right. So saying the remainder goes to 0 means that these two things just get closer and closer to each other. The function and the Taylor polynomial get to be very close to each other. And so that means this goes to 0. If it goes to 0, looking at this expression, if we take the limit as n goes to infinity, this thing becomes a 0. These two things are then equal to each other, okay? There's a lot going on here. One of the things I'm kind of glossing over is the fact that this remainder also depends on x. At each value of x, you have a different remainder, right? On those graphs, we saw the function was very close to its Taylor polynomials at some point, and not as close in other places. It's a tricky business to prove that these things are equivalent to each other, which is why we're not going very far down this road. So in general, what will happen is we can often find, this is basically the condition on having a Taylor series. So let me say this with, what could I say? Let's say it this way, if R sub n of x goes to 0 as n goes to infinity, when x minus a is less than r. Remember, this is our interval convergence idea. So often this only works on some interval. The last one we looked at, it worked everywhere, but some of them will have some small interval. Then f is equal to its Taylor series. When x minus a is less than r. Okay, so it's really just what I was saying up here, but adding in the fact that this might also depend on x. Okay, it often depends on x. Okay, so to show this, we implement a tool that I am not going to go into the details of why this is true, but we have something called Taylor's inequality, which just says this: if the n+1th derivative of our function is less than or equal to some number m whenever x minus a is less than d, some number d, then the remainder has to be less than or equal to that number m over n+1 factorial times x minus a to the n+1. Okay, so in other words, sometimes we can pin our next derivative under some number, right? So for instance, the case if we were looking at trig functions like sine or cosine, you can always say their derivatives are less than 1. And so then you get a value for m here. And you can see that if you have some value like m, if you can pin that derivative under some number, then this factorial in the bottom, as n gets larger and larger and larger, is generally going to make this thing shrink pretty quickly, right? It's just that we can't always pin m, and so that's why we see some series where we aren't able to have this work everywhere. Sometimes it depends on this term being small. So we won't do many examples with this. This is a pretty complicated idea that's kind of a little bit beyond the scope of this course, so I'm happy to talk, take video requests if somebody wants to go into more detail on this, time allowing. But let's do that just for the function we've been looking at in this video, e to the x. Let's take advantage of this tool here and see if we can show that e to the x has a Taylor series and that it's equal to, let's show that e to the x is equal to its Taylor series for all real numbers. Okay, so, oops, that's not what I want to write. E to the x is equal to sum n equals 0 to infinity of x to the n over n factorial. That's what we're trying to show, okay? So I want to use Taylor's inequality to show this. So what can I do? Well, a few things. I can say, since f of x, let me put a question mark there since we're not quite sure that that's true yet. F of x is equal to the nth plus 1, oops, I want to say this. The nth plus 1 derivative of f of x is e to the x, right? Every derivative of e to the x is e to the x. So the nth plus 1, whatever term we're at, e to the x. Okay, so for any value, for any real number d, we can say the nth derivative is less than or equal to e to the d if x is less than or equal to d. The absolute value of x is less than or equal to d, right? So this is just this line, right? Think about the exponential. If we pick a number d, the exponential increases. For all values of x below that, our function is going to be smaller. Okay. Okay. So I guess d would be positive number here. Yeah, we'll take d to be positive, and then it covers the negatives because they're going to be certainly less than the positive values of d. So let's say d is greater than 0. I think we need that. I don't want to get tied up in that detail at the moment. So then according to Taylor's inequality, I've got this first line. I know the remainder has to be less than or equal to e to the d over n plus 1 factorial times x to the n plus 1. Oh, and I forgot my absolute value. Well, let's take the limit. This means that the limit as n goes to infinity of the remainder has got to be less than or equal to the limit as n goes to infinity of e to the d over n plus 1 factorial times the absolute value of x to the n plus 1. Well, what is this thing here? Let's do a little bit of algebra. E to the d is just a constant. And now I have x to the n plus 1 over n plus 1 factorial. Now, this limit here, we're going to get this in a pretty clever way. Let me go back to getting a bit disorganized here. We proved a couple of moments ago, somewhere that seems to now be gone from me, so maybe I'll just write it again. We proved a few minutes ago that this series right here converged for all values of x, right? We didn't prove that it was equal to e to the x, but we did prove that its radius of convergence, we used the ratio test to prove that the radius of convergence for this was all real numbers. A series only converges if the values of if the sequence of its terms goes to 0. This is the sequence of its terms. I mean, I've gone to n plus 1 and n plus 1, but it's the same thing. We're going to infinity, so they're both getting large at the same time. These must go to 0 because this series converges for all x, okay? Which means we get 0 times a constant or 0. In other words, the remainder for the Taylor remainder for this series that we came up with goes to 0, which was what we needed to show to say that our Taylor series was equal to our function, okay? In other words, what we can now say is e to the x is equal to n equals 0 to infinity of x to the n over n factorial for all real numbers. Okay, so this is a pretty interesting and powerful notion for us, that we can write a function like the exponential as this infinite series, right? Again, we're not getting into too many details at the moment about why this is important, but I have mentioned that there are plenty of contexts out there where it turns out using an infinite series is an easier way to deal with something than using the function itself. Or in the instance of computing, it's a way that we can get calculators to compute e to the x for us, right? You know, we might not know how to do e to the, or a computer might not know how to do e to the 1.795, but it does know how to multiply numbers and divide numbers and add numbers, right? That's something we've already been able to program them to do. And so we can compute series up to a point, right? The other big idea that, again, we're not getting into lots of detail about, but this is actually involved, the remainder goes to 0 as n goes to infinity, which means as we go further and further out in those nth degree Taylor polynomials, the difference between the nth degree Taylor polynomial and the actual function gets smaller and smaller and smaller. And so if you go out far enough, your error is minuscule. So if you're trying to do a calculation, like on a calculator, and you want to display 8 decimal places of accuracy, you can figure out how many terms you need to compute to get that. And so that's one of the ways we actually compute things with our computers. Okay. I am not going to ask you guys to prove things like this on quizzes and exams. I may do that in a project or homework or something like that, where you can look at the examples in the book. And so we're mostly going to assume, when I ask you to compute a Taylor series, you can assume that it exists, and I just want you to go through the process of computing it, okay? So with that in mind, let's do 2 examples to finish this off, where all we're going to do is compute the Taylor series, not worry about proving that it has to exist. Okay, so let's look at the function f of x equals the natural log of 1 minus x. And I want to compute this series at 0. Okay, we're centered at 0. Okay, in other words, I want to find a series like this, right? So that these two are equal. We might find some interval of convergence. We'll see what happens when we compute the series. You actually might remember we stumbled onto this series using the geometric series previously, but we're going to build it from scratch this time and see if we get the same thing we got a couple videos ago. So remember, what I'm going to use here, all I need to do is find out an expression for C sub n. That's really all I need to know. And C sub n is equal to the nth derivative at a over n factorial. In this case, that's the nth derivative at 0 over n factorial. Okay, right? Not always at 0, but in this case, it's at 0. So we're going to go, this is how I usually organize. I start by writing out the function. I write the first derivative. So our first derivative here is going to be 1 over 1 minus x, and then a chain rule gives me a negative 1 out front. And instead of writing 1 over 1 minus x, I'm going to write it this way. This is typically how I write things, especially when I'm doing Taylor series, and you might see why in just a second. Let's compute the second. I usually compute 3 to 4 derivatives to see if a pattern emerges. That's usually enough. It's sometimes difficult to tell exactly what the pattern is going to be in the beginning. So let's do the second derivative. I get a negative 1 coming down front. That makes this positive. I'll get 1 minus x to the negative 2, but then I get a negative from the chain rule in here, making it negative. So now I have negative 1 minus x to the negative 2. The third derivative, my negative 2 comes down and becomes positive. I have 1 minus x to the negative 3, but then I have a chain rule that puts a negative in front again, right? So this I can already see is going to keep happening. I'm going to get negatives from the powers, canceling with the negative that's already here, and then a negative from inside on the chain rule is going to make it negative. So I'm always going to have negatives. Let's do the fourth derivative. 3 comes down. I'm going to get a negative, a negative, and a negative. I'm going to end up with negative. So I have negative 3 times 2, 1 minus x to the negative 4. Okay. I also usually don't multiply numbers together, right? I don't care about what the actual number is. What I'm trying to come up with is a simple expression. And I can kind of see what's happening here. Let's just do one more to be clear. If I take the fifth derivative, I'm going to get negative 4 times 3 times 2 times 1 minus x to the negative 5, right? In other words, what it's looking like is the nth derivative. What do I have? When I had the fifth derivative, I've got a 4 factorial sitting here. When I had the fourth derivative, I had a 3 factorial. Third derivative, 2 factorial. Second derivative, 1 factorial. First derivative is a 0 factorial. This one doesn't quite line up with the pattern, so we'll deal with that one in a second. This often happens, especially with natural log. You get these patterns, but the first one doesn't quite line up because it's in such a different form. So what do we get? What this looked like was a negative n minus 1 factorial 1 minus x to the negative n, right? all of these abide by this rule. The first one's a little bit different, okay? So let's now, I usually make a second column where I evaluate what my derivatives are at 0. So f of 0 is the natural log of 1, which is 0. Okay, so my first term, my constant term is 0. And that's pretty nice. It wasn't fitting with the pattern. What I'm going to do is just not even write, we're not going to have a 0th term because the constant term is just 0. We only have to start at the first derivative. F prime of 0 is -1. F double prime of 0 is also -1. The third derivative at 0 is -2, right? Notice what's happening. We're putting in 0, the denominator is always 1. It doesn't matter what power we take it to, it's just going to be 1. So these constants out front are just what the value of the derivative is. The fourth at 0 is -3 factorial. 3 times 2, of course, there's times 1, but it doesn't do anything. The fifth derivative at 0 is -4 factorial. So the nth derivative at 0 is looking like -n-1 factorial. Okay. So what does that mean? Let's just come right up here. The nth derivative at 0 is -n-1 factorial over n factorial. Right? What's n-1 factorial over n factorial? I've got my negative. It's just 1 over n. Okay. So putting this all together, I have the natural log of 1 minus x is equal to, now here's what I'm going to do. All of my terms, the coefficients fit into this pattern, except for the first one, right? When n equals 0, 1 over 0 is not 0. There's an easy fix. I just start at 1. I just skipped over the 0 term because adding 0 doesn't do anything. And I get a series that looks like, so I'm putting in for c sub n, -1 over n times x to the n. So it's going to look like -x to the n over n. That looks a little clunky to me, so I'm going to pull that negative out front. And I get n equals 1 to infinity of x to the n over n. Okay. Now, we have one more step to do. We've got to take a look at the radius of convergence. Let's use the ratio test. So I want to compute, we're going to be taking absolute values, so the negative's not going to matter. I'm going to have the nth plus 1 over the nth term in absolute value is going to be x to the n plus 1 over n plus 1 times, we'll have n over x to the n, which is going to be equal to n over n plus 1 times x. Okay, so the limit as n goes to infinity of n over n plus 1, I'm just going to separate these to make it a little easier. This thing goes to 1, so we get the absolute value of x. Remember, our ratio test tells us that this thing will converge whenever the limit is less than 1. So we know that this converges whenever x, the absolute value of x is less than 1, or x is between -1 and 1. Okay. We did this one in a previous video, so I'm going to go through the last part pretty quickly. We have to check the endpoints. When x equals 1, ignoring the negative out front, but that doesn't change whether or not the series converges. When x equals 1, this is the harmonic series, which diverges. But when x equals -1, it's the alternating harmonic series, which converges. And so I can write the interval of convergence as -1 to 1. Okay. So let's do one last thing. Let's take a look at This is the interval convergence for this series. So natural log of 1 minus x is equal to this series on this interval. Let's take a quick look at the graph of this. Okay. There you are. Okay. This is from a previous video. We actually already looked at this one, but we computed it by taking the antiderivative of the geometric series. But now we came at it a different way, but we ended up with the exact same series, right? If you look over here and refer back to an older video, you'll see that we got the same series we got there. And in the same way, this, as I add terms, I'm matching more and more closely with that green function, only in this case, I'm only matching between -1 and 1. At 1, my function has an asymptote, so I can't match with it there anyways. Here, I am matching eventually at -1, but all I can show you is that we're getting closer by taking more and more terms. Okay. I think I promised you another example, but I think I'm going to put that into another video. There's enough in this video. I'll do a second video on this topic that is nothing but examples of building these things and finding their intervals of convergence. All right, thanks everybody. I will see you next time.